Okay, well, it's a minute past the top of the hour, so we'll go ahead and get started. I want to welcome everybody today to our USDA REAP, Rural Energy for America funding for geothermal energy projects. We have a group of presenters today. We have our researchers from the National Renewable Energy Laboratory that will be presenting on the technology of geothermal. And then we have myself, Brenda Heinen, and John Beeler in the background from USDA Department of Agriculture to answer any questions you may have on the REAP applications process. Next, please. So the agenda today, we'll do a little welcome. We'll have a webinar overview and an intro to REAP. And then next, we'll have a geothermal discussion from NREL for about 40 minutes. And then we'll move into a geothermal applications for REAP for an additional 15 minutes. And then at the end, as time allows, we'll have a Q&A to answer any questions you may have of us at USDA or our NREL partners. Next, please. So with this, the USDA REAP, Rural Energy for America, and RAISE, we have a joint initiative between USDA Rural Development and our DOE and NREL partners, National Renewable Energy Lab. Next slide, please. My name, by the way, Brenda Heinen. I'm the Western Regional Energy Coordinator and Western Regional Coordinator for the Western states. I have 17 states that I cover out west, and what I primarily do is assist the states with the Rural Energy for America program. One of the initiatives we have right now is our RAISE initiative. It's the Rural and Agricultural Income and Savings from Renewable Energy Initiative, which will provide savings and additional revenue sources for small agricultural producers and businesses in rural America. Since 1981, the nation has lost nearly 545,000 farms and 155 million acres of former farmland. The nation has enjoyed record farm income in recent years, but the income has been concentrated among 7% of farms that cumulatively account for 89% of the income. In the face of increased costs, competition for land use, and consolidation, small family farmers shouldn't have to work twice as hard. We should always find ways, or we should find additional ways for them to generate revenue from the land. Based on our collaboration between Department of Energy and Department of Agriculture, this effort will advance opportunities for small and mid-sized farmers to enjoy energy savings and income from underutilized renewable energy projects. We will pilot new and innovative business models for farmers, rural electric cooperatives, and developers that utilize distributed energy resources to generate revenue for farmers. We want to lead to 400 individual farmers deploying small-scale wind projects within 5 years using REAP. So this is a summary of the RAISE initiative. Next slide, please. Today is our geothermal webinar. Please note that we will have an additional webinar upcoming on September 19th from 9:30 a.m. to 11 a.m. Mountain Standard Time, covering hydro projects. Next slide. Here are some additional relevant resources. We have a new NREL REAP website. So on the NREL webpage, there is resources for REAP. If you go under the Rural Energy for America tab, under technical assistance, you will find the slides to our webinars that are being held and the recordings. There are also other tools out there available for your use as well. Also on this slide, there is a link for the REAP program, so you can find information about REAP and where the application is located if you are looking to apply for a REAP grant. REAP grants, by the way, are 50% grants made to agricultural producers and rural small businesses to install renewable energy systems and energy efficiency improvement type projects. And With the RAISE initiative, just note we are looking for underutilized technology applications, and geothermal falls under that category. We at Rural Development are prioritizing our reviews of underutilized technology applications. So if you're interested in submitting geothermal application, now is a good time to do so. If you have questions, we do have an energy coordinator in each state. So we've listed a link here. If you have questions or a project in a specific state, you can contact your local rural energy coordinator to answer your questions you may have on the program. And then on the bottom, we've also included a link to frequently asked questions with REAP. Next, please. Some housekeeping notes. At the bottom, you will notice that you'll see a Q&A function or a chat. You can ask your questions there and we'll answer them during the webinar. If time allows, we can also ask those questions verbally at the end if we don't get to all of the questions. The following information and best practices are recommendations based on NREL's experience in this area and are not meant to supplant any REAP application requirements. NREL staff cannot answer any specific application questions, but each rural development office can, and that list of rural energy coordinators has been provided on the previous slide. Next. So now we'll move into the geothermal energy fundamentals. So we'll bring up our first speaker at NREL.
Yeah, thank you, Brenda. Welcome all. My name is Stephanie Davalos. I have been at NREL now for 2 years. My background is in geology, and I have more than 10 years of experience in the geothermal exploration of geothermal energy, more specifically in the high temperature resources, but my PhD and now at NREL, I have been focused more in the low and temperature resources. I'm going to explain some of the geothermal energy fundamentals and some of the different geothermal technologies. So next slide, please. So I think an important concept for understanding geothermal resources is the geothermal gradient, because the geothermal energy is related with the temperature. And where this temperature of geothermal energy comes, it's coming from the air, yeah? So basically the geothermal gradient is the rate at which the air temperature increase as you go deeper underground. On average, this gradient, it's about 25 to 30 degrees Celsius per kilometer. But it depends also for the location, the geology, and the presence of hot springs or volcanic activity. You can have some anomalies in the earth that increase that geothermal gradient and allows to utilize that geothermal resource for also power generation. Next slide, please. So also let's keep in mind that not all the resources are coming from the inner core of the earth. There are some geothermal resources of low temperature that are coming from the sun, being stored in the earth surface. So that heat from the sun, it's basically absorbed in the soil, and you can store that temperature. Basically, these geothermal resources are shallow and are low temperature geothermal resources. And there are some geothermal technologies such as geothermal heat pumps that we're going to explain in a couple of slides after that you can utilize these shallow geothermal resources. Next slide, please. So here in this diagram, I just want to highlight the geothermal energy full potential. So basically, geothermal in the past, it was related more with the generation of electricity, the power generation, and as I already mentioned, this geothermal resource, it's related with high temperature resources. You need to go deeper in the subsurface of the earth. But nowadays, we are interested also in the shallow geothermal resources, such as geothermal heat pumps that you can use for heating and cooling buildings or districts, and also the full potential. Also, you can use geothermal for storage energy in the subsurface, and also you can use geothermal with a hybrid as an hybrid technology, for example, combining with solar panels. Um, Next slide, please. So as I already explained, the geothermal resources depends of the temperature of the resource that you can find or you can extract from the earth. Here in the right side, you have like a thermometer that is showing the different types of direct uses. So I'm gonna start with the lower. So when you have like low temperature resources, basically like less than 50 degrees Fahrenheit, you can call it heat exchange, and the technology used is basically geothermal heat pumps. This energy is gonna be like very shallow, so basically it's in the ground. Uh, you use the soil basically. Um, Once you are starting like finding more temperature, so such as more than 100 degrees Fahrenheit, you can start using this heat extraction uh, for other like direct uses. You need water for these ones, for example, hot water that has that temperature to like use for greenhouses, fish farming. Also, you can use like these direct uses for heating and cooling as well. Once you are finding like higher temperature resources, you can like generate electricity, and there are different like geothermal plants depending of the different temperatures like, but basically the generation of electricity, it's when you find a resource of more than 150 degrees Celsius, or in this case, it can be 250 degrees Fahrenheit. And for sure, you need to go deeper into the subsurface to like find those temperatures. Okay, next slide, please. Here in this slide, I just want to highlight the importance of the geothermal resources in the future of decarbonize the United States. For electricity, we are expecting to generate 8.5% of the US power by 2050. That will be like allowing to avoid like more than 500 uh, million metric tons of CO2 into the atmosphere. And also there are like these heating and cooling applications that we can develop more than 23% of increase of these ones in the market by 2050. And I want like to highlight here that heating and cooling, it can be using geothermal heat pumps or direct uses. As direct uses, I mean like finding the hot water. But basically, the geothermal heat pumps have the advantage of like is a technology that you can use like in the whole country. It's not like limited by finding the hot water and different like temperatures of this fluid, depending of the geology and other like aspects of the resource. Okay, next slide, please. I want to explain very briefly, like in terms of technology, this geothermal power technologies. I just gonna explain the conventional geothermal resources because that's the one that the technology is already like using in the market. So it's already proven, it's already there. Uh, so the limitation of this technology, as I already mentioned, is that it's just focusing in a different like areas of the country, and most in the western part of the US, where you can find these like high temperature resources. Um, and I want to comment here that also for this technology, you need like to have a heat source, volcanic, it can be a volcanic source that's why you have these high temperature resources. You need to have also fluid accessibility. So you need to find like water, hot water. You need permeability to be able to like this water coming to the to the surface or shallow surface, and you can extract this water. And sometimes you also need a seal, like a layer that like creates like a trap that avoids that heat it's losing, and that water is losing as well. So um, I want to explain like very fast like how these plants, different geothermal plants work. Um, Basically, the dry steam power plant. So you need to like find this resource in the subsurface where you have uh, hot water, but this hot water have a section that it has been like converted in steam, and this steam is trapped in the subsurface. So basically, you need to drill a well, find this steam, and this vapor is gonna rise to the surface um, from this like well. Once you have this steam, the steam is gonna like move the turbine, and it's gonna generate electricity. Yeah. Um, After passing through the turbine, this vapor is gonna be cooled, and it's gonna be condensed, and you're gonna reinject that um, liquid now to the reservoir to maintain the pressure of the reservoir, and it's like a continuous like cycle like that. The flash steam power plant, the one in the middle in this slide, um, it's very similar to the dry steam, but you are using the resource of hot water in the reservoir. And once you have like this well drilling and extracting this hot water, um, due to the pressure drops of this water, once this water is reaching the surface, the water flash into a steam. So you have like a proportion of like water and another portion of steam. And you're gonna use the steam to like move the turbine and generate electricity. Uh, the water, the liquid is gonna be like reinjected into the reservoir again. And the steam that it was using in the turbine is also going to be cool, converted into like water and reinjected again as well. Now the binary cycle power plant, this one uh, it's also like Nova's organic ranking cycle, and you can use geothermal resources of like lower temperature. So basically, what you have is uh, you have a you extract the water, the hot water from the reservoir, but it's not gonna be super hot. So you're gonna use another like secondary fluid that it can be like isobutane um, that has a lower boiling point. So basically you use the water from the reservoir to heat that isobutane that is gonna be like converting to a steam, and it's gonna like move the turbine, create electricity, and you're gonna reinject the water from the reservoir, but the isobutane is just in a closed loop there in the heat exchanger. Okay, next slide, please. So I'm gonna start explaining some of the geothermal low temperature technologies because I think that one is probably the ones that you are more interested in, like apply in your rural areas. So next slide, please. So we can divide these low temperatures in direct uses and geothermal heat pumps. Here I'm going to explain the direct uses of geothermal. So basically these direct uses is, as I already mentioned, you need like hot water uh, to like use these geothermal resources. Basically the hot water, you can have like favorable areas where you can like find these um, resource, and basically most of the hydrothermal systems are located in the western part, but that doesn't mean that you cannot have those in the central or in the east, but they are more like dispersed in there. Um, so basically the range, as I already mentioned, it's between like 100 degrees Fahrenheit and all the way to 250 degrees Fahrenheit for the direct uses. Next slide. So I want here like to show like what kind of like direct uses you can you can have with these like hot water resources. This is like another like type of like technology that we call it cascade geothermal system. So it's basically like extracting that hot water, and you can use the different temperatures for various applications, creating like a sequence of cascade. Um, so you can have like a resource of high temperature or medium temperature, basically. You can start with electricity generation, but also if you don't have like that um, high temperature resource and you have medium, you can start with like heating um, applications. And then once the temperature of the fluid is lower, so you can utilize that for agricultural purposes, such as greenhouses, heating and fish farming, um, drying crops, etc. Yeah, so this effective approach maximizes the energy use from a single geothermal resource, and it's very like environmental friendly and cost effective. Okay, next slide, please. Here is just an example of how we can use like these direct uses. Here is combined with also another like technology that it can be like geothermal heat pumps, but I want to mention here that there are like different direct uses. You can do shallow geothermal heat and cooling technologies or deep geothermal heating technologies with these direct uses. Uh, the difference is like you can like have like a shallow aquifer where you can like use that like temperature to like cooling or heating like buildings or districts. And in the deep geothermal heating, you can like drill a little bit deeper to find the temperatures that you want to also like heat and cooling like buildings. Basically, most of the direct uses are gonna be open loop technologies. Uh, these um, these wells for the direct uses like are gonna like the it depends of where you find the resource, but you can like have 150 to like 2 kilometers of depth. Okay, next slide, please. So now I'm gonna talk about the geothermal heat pumps. These geothermal heat pumps are the ones that are you don't need like to go very deeper. It's just like in the shallow part of the earth. So basically, you are finding this resource in the ground. Um, so it has a high efficiency due to the constant and moderate air temperature that you can storage in the soil, and you can use this technology for cooling or for heating. And these resources, basically, you can use this resource like with temperatures of less than 50 degrees Fahrenheit. We also know this technology, it has like different terminologies, not terminologies, but different like names that you can call them, such as ground source, ground coupled, geo exchange, air coupled, air source, or water source. Next slide, please. So here I just want to explain how like these geothermal heat pumps work. A heat pump operates by transferring like the heat from one place to another using a refrigerant and different components like the compressor, the condenser, the expansion valve, and the evaporator. Um, when you have the heating mode, the refrigerant absorbs the heat from, in this case, from the soil, from the ground, as it evaporates in the evaporator. Uh, this low pressure gas then moves to the compressor, which raises the pressure and the temperature. The hot and high pressure gas then flows to the condenser, where it releases heat into the home or into the building as it condenses back into a liquid state. This refrigerant then passes through an expansion valve, reducing its pressure and allowing it to cool down before returning to the evaporator to repeat the cycle. In cooling mode, the process is the reverse, extracting the heat from the building or from the house and expel it into the ground, basically. Okay, next slide, please. So here we have like different like configurations of how these geothermal heat pumps work. So you have basically three types. They are closed loop, all of them, but the first like figure on the top left, it's a vertical closed loop. The one in the right is horizontal, and the one like below is a closed loop system using a pond or a lake. Okay, next slide, please. So basically the vertical borehole heat exchanger are the most common form used for the geothermal heat pumps. And typical you need depths of 300 to 500 feet, but could go deeper as well. You need just a mobile drill rigs like the ones that you use for groundwater, and the borehole diameter can vary between 4 to 6 inches. Um, and also there are different type of drilling technologies that are available to like create these like vertical boreholes for these heat exchangers. Okay, next slide, please. So there are different like types of like vertical boreholes. We have the U-tube that is basically a single U-tube that is a pipe connected with a U-bend at the bottom, as you can see in the figure in the left side. It's a closed loop, no fluid exchange with the environment. The area between the U-pipe and the borehole wall is grouted to prevent the groundwater contamination. There is another type that is a double U-tube that is basically two or more U-pipes that can be connected in series of parallel. Decreases the resistance to heat to transfer with the soil. And the other one is the coaxial. That is a fluid pumped through the center of the pipe and an annular region. And this one requires a casing. So next slide, please. So as I already mentioned, there are some of these like important like aspect of the vertical boreholes. The diameter that it can be like 4 to 6. The pipe that it can be a high density polyethylene pipe, and you have a grout that it can be like a clay or bentonite mixture to like maintain the thermal conductivity in the soil as well. And you have a fluid that it can be a water bio inhibitor that can be used by in cooling only applications as well. So the next slide, the horizontal heat exchanger, this is another type. This one, it's a little bit shallower, so it can be installed in top of 3 to 10 feet of soil. You need a higher surface area to make this installation. It has a lower cost to install because you don't need to drill. The performance is lower than the vertical system because the soil temperature is closer to the ambient air temperature during the year. Next slide, please. So the surface, this is a surface water heat exchanger where you can use like a pond. If you have like a lake or a pond like in the surface, that you can use it for this heat exchanger. It can be used effectively when this water surface is available, and if designed appropriately, can be removed. You can remove it and do the service for these ones. Sometimes need freeze protection if it's if you have like lower temperatures. Okay, next slide. Let's skip this one just to save a little bit of time. Next slide, please. So let's talk a little bit about the benefits and considerations for these geothermal heat pumps systems. So they are very efficient. I think it's higher than the air heat pumps. It has low maintenance, heating savings. Also, this technology helps to decarbonize the country. Some of the important considerations is the space strategy. So as you already see, the vertical doesn't need a lot of space, but the horizontal loops needs big space, so you can use parking lots, buildings or green spaces to install this type of technologies. The climate zone also, it's an important aspect. So because the climate zone is gonna also drive the building or the home consumption of heat or cooling. Also, the geothermal heat pumps depends of the design and the requirements depending of the location where you are installing. And the soil properties is another important aspect here. Because also the soil properties is going to depend the thermal conductivity and if the soil is moisture or is dry. So you need to consider all these to design your system. Okay, I think that's what I have now. Diana is gonna explain a little bit of some examples of these geothermal heat pumps. Diana, thank you. The floor is yours.
Thank you, Stephanie. So hello, everyone. My name is Diana Cerro-Alar, also researcher here in NREL, geothermal researcher. In the next slides, I am going to show to you some applications that they are public out there for agricultural activities. And I just want to have here a disclaimer. Is on my knowledge, none of these they receive any technical assistance or something from NREL. This is information that is in the public, is available for everyone, but very interesting application. So next. So one of the first one is a farm that is in the northern of Michigan, where they use geothermal heat pumps to heat a greenhouse, but also to cool the fridge. So they use the two application on the end there, the heating and the cooling. So here there is some specificities about that. The idea is to keep always the greenhouse in a 90 degrees Fahrenheit, the floor of the greenhouse. And this is claimed there in the website. If you look for Conveyo Farm in northern Michigan, the efficiency and the cost effective of the systems. While during summer, they were paying before thousands of dollars for conventional methods. With these systems, they lowered that to hundreds a month. So it's efficient. It works for, again, heating and cooling in the zone in the northern Michigan for summer and winter. Another one, the next one. So this is an example for a greenhouse in Nebraska where they grow citrus fruit, some figs, even other type of fruits there in this greenhouse. What they use there is a system that is not only coming from the geothermal, but also coupled with other components to take advantage of the solar heat that they are receiving during the winter. And always to keep that greenhouse above 28 during winter. And one of the resource from the ground is the heat on 53 Fahrenheit there, and only 8 feet of deep. So also it's mentioned that it has some indirect benefits to decarbonization for transportation. When you think about like transporting all this fruit or produce to other parts instead of produce it in the same place. So remove this transportation component. So other benefit of these applications. Next. This is a very special example. This is for an educational camp that is in Georgia, the southern part of the country. Here they use different type of renewable energies for the education and for the sustainability for their activities. And the geothermal ground loop that they use is actually is groundwater that is strategically placed in wells to help the condition of the air in the building. So it's another application of these technologies. So we see heating and cooling, we see keeping some temperature during the year, and also help with other type of activities important for agriculture activities like the air condition. Next. Okay, so when we talk about like project development and cost, next, we are comparing a little bit with other systems sometimes. And here are some considerations for the cost. So the ground heat exchange, that is the system, is the biggest part of the cost. As you saw, and Stephanie showed us, it has drilling, it has some activities that they are out, and that part, it is the biggest part of the cost. The actual ground source or geothermal heat pumps, yes, are more expensive than an air source heat pumps. However, it comes with other benefits and savings in the long time. If the system that is designed needs circulation pumps or other type of additional components, that can add a cost to installation and operations. When we talk about lifetime, so the geothermal, the ground source or geothermal heat pumps have a lifetime of 20 to 25 years, while the air ones have something between 10 to 15 years, so something to compare. And the geothermal, the ground heat exchanger have lifetimes of probably more than 50 years. And the maintenance is one of the benefits. The maintenance for the geothermal heat pump systems need less or minimal maintenance. And if it's designed and installed properly, the ground loop, it requires very, very minimum maintenance on that. So it has to be a lot with the design of the full system and the conditions. Next. Okay, so here next, I would like to show you some resources. One is systems, softwares that are used for modeling, to design or modeling how in these heat pumps, the soil properties and how is the system. So there are now in the market the GHD Designer. This is an open source software that is available in GitHub. If you Google this one, you will find it. It's open source. It's developed by researchers and is in continuous development, which is a good thing for designing tools because it's improving. However, this one specifically will need Python knowledge, and it doesn't have yet an interface for the user. There are another two that they are commercial. They are not open. They will need a license. The GLH ePro, and actually we have seen in applications that applicants use this for their systems. And it has good benefits to use this. They have different type of geothermal heat pumps designs or different types in their databases to compare, for example, and to include in the system. Is comparable also with the ground loop design or GLD software, also a commercial software there available for designing this type of systems. Next. And in terms of the resources, some basic standards that you should look for or definitely get information from there. One is the International Ground Source Heat Pump Association, or IGSPA, where you are going to see information as standards, as training for different type of phases of the systems, for contractors, for designers. Also the International Association of Plumbing and Mechanical Officials for the design standards. Next. Other type of resources is the Geothermal Exchange Organization. One very important part here to name is that in the GeoExchange, actually, they have a forum where people talk about like their systems, and it can be, details about that or questions. It will be a good resource maybe to try to see something that is regional or very local, applicable to your projects. So I invite you to check that one. And the American Society of Heating, Refrigerating, and Air Conditioning Engineers also, for different type of standards and design handbooks. Next. Thank you.
Hello, thanks Diana for your presentation. My name is Hyunjun Oh. I'm a geothermal energy engineer in geothermal research program at the National Renewable Energy Laboratory. My background is in geological engineering, and I am working some projects for techno-economic analysis of different types of geothermal applications, from geothermal heat pump to deep direct use applications. I am supporting a technical assistant program for reviewing your RIP proposals, particularly the technology and design part. Today, I want to share some guidelines and tips to help your geothermal applications for RIP. Next, please. The technical report consists of 8 subsections, from qualifications of the project team to operations and maintenance. I will present general information and guidelines for each subsection. Next, please. First section is the qualifications of the project team. In this section, the applicant describes the project team, their professional credential, and relevant experience. The description shall support the key service providers in the project team, have the necessary professional credentials, licenses, certifications, and relevant experiences to develop the proposed project. The applicant may consider including biographies for key service providers, a short list of relevant projects, or one example project that the applicant may want to highlight. Next, please. Next section is agreements and permits. In this section, the applicant describes the necessary agreements and permits required for the project, including any for local zoning requirements. For example, drilling boreholes at a depth deeper than XYZ meters may be restricted in the specific area. Interconnection agreements and power purchase agreements are necessary for all renewable energy projects electrically interconnected to the utility grid. Next, please. Resource assessment, as Estefania and Diana presented, geothermal resource potential may vary significantly regionally and seasonally. So in this section, the applicant describes the quality and availability of geothermal resources and the amount of energy generated through the deployment of the proposed system. If the applicant considers deep direct use applications, the geothermal resource potential at a certain depth, as Estefani presented, may be significant. On the other hand, if applicants consider geothermal heat pump, ambient conditions and soil properties may be significant. Next, please. Next one is design and engineering section. In this section, the applicant describes objectives of the project, what system the applicant wanted to propose, and how the system will be used for your system. And then the applicant needs to describe the design, engineering, testing, and monitoring details with supporting materials. As I shared briefly before, deep geothermal research potential may be supported from the literature review or preliminary monitoring data, or shallow subsurface temperature or soil properties could be supported. And then lastly, in this section, the applicant identifies all major equipment is commercially available, including proprietary equipment, and justify how this unique equipment is needed to meet the requirements of the proposed design. Next, please. So here are some examples that can be obtained from the literature review. If you can conduct preliminary field test to measure soil test, that would be an option. And also the applicant can consider literature review to collect the necessary information about soil type, soil thermal conductivity, and water retention characteristics. Next, please. Next section is project development schedule. In this section, the applicant describes the overall project development method, including the key project development activities and the proposed schedule for each activity. The description shall address cash flow for the project development. Details for equipment procurement and installation shall be addressed in this section. Next, please. Next section is equipment procurement and installation. So in this section, the applicant describes the availability of the equipment required by the system. The applicant describes the plan for site development and system installation, including any special equipment requirement. In all cases, the system or improvements shall be installed in conformance with manufacturer's specifications and design requirements, and comply with applicable laws, regulations, agreements, permits, codes, and standards. Next, please. In the last section, the applicants describe the operations and maintenance plans. Specifically, the applicant describes financial performance of the proposed project, including simple payback estimation. The description addresses the project initial capital cost, operation and maintenance cost, and revenues, such as applicable investment and production incentive and other information to allow the assessment of the project cost effectiveness. Next, please. So yeah, I shared brief guidelines to help your proposals, and please feel free to ask any questions.
Does anyone want to raise their hand and ask a question? I know we did have one question in the chat about the slides, and those will be available on the NREL resource webpage. They do take a week or so through a clearance process, but then they'll be available to all the participants and others that reach out to that webpage to listen to the recording. Okay, well, I'm not seeing any other questions in the chat. Oh, we do just have something coming in. Okay, I think this question is internal, USDA. How many geothermal apps are we getting? And right now, the answer to that would be, I don't have the exact number on hand right now, but I can get that to you and get back to you. But we do have some geothermal projects applications. I don't know if it's a dozen or more, but we do have them coming in from states. Okay, I'm not seeing any hands. Just give it a minute or so to see if there's any other questions. Coming in. Okay, well, not hearing any. If there are any follow-up questions after today, please reach out to your state energy coordinator in your state for any REAP application questions. And then if we have any technical questions, the state can reach out to one of their regional coordinators, and then we can ask an expert a question through our technical assistance contract that we have with NREL. So at this time, I would like to thank all of the presenters. This was very interesting and helpful information for us to learn about and have the opportunity to submit geothermal applications in the REAP program. So I would like to thank you. And then this concludes our webinar for today. Thank you.
Thank you.
Yeah, thank you all.